Hello everyone, welcome back. This is our second lecture for Chapter 1. In this lecture, we will focus on defining basic terminology and explaining some of the foundational concepts of statistics, specifically population versus sample, parameters versus statistics, and descriptive versus inferential statistics. So let's begin. For virtually any question that you may want to investigate about the world, you have to center your attention on subjects. Subjects are the things or entities that we measure in a study. Subjects could be individuals, schools, countries, days, animals, plants, exam scores, particular groups of people, rock specimens, etc. Some examples of questions that you might ask. What do Americans think about the president's foreign policy? What's the prognosis of breast cancer patients taking a new experimental drug? How many hours of studying does it take to pass a statistics course with a C or better? In each of these examples, a question is asked, and in each case, you can identify a specific subject that is being studied. The American people, all breast cancer patients, and statistics students. This group of subjects of interest that you're interested in is called a population. Population is all subjects of interest. The population contains all past, present, and future members of the group. So we usually consider it to be infinitely large. And populations can also be hard to define. Take, for example, the research question about whether babies sleep better with music. This is a good example of how difficult defining a population could be. Exactly how would you define a baby? Under 3 months old? Under a year old? And do you want to study babies only in the US? Or do you want to study all babies worldwide? The results might be different for older and younger babies, American babies, and babies from other parts of the world. And also, are you going to observe all of the babies? Some other examples of populations could be all the people in a country, like census information, students in this statistics class, all M&Ms in a bag of candy. Can you think of your own examples of populations? So you can take a minute, think about some of your own examples here. Great. To measure an infinitely large population would take too long and cost too much money. We usually do not have the time nor the resources to study an entire population. So instead, we select a sample from the population. A sample is a small subset of individuals selected from a population. A sample is intended to represent the population of interest. So here's a way to think about samples. How many of you have cooked or sampled someone's cooking? Let's say you just made soup and you want to sample some of that soup. What do? Well, you stir the pot, reach in with a spoon, take out a little bit of soup, and taste it. Then you draw a conclusion about the whole pot of soup without actually having to taste all of it. If your sample is taken in a fair way, you didn't just grab all the good stuff, you will get a pretty good idea of how the soup tastes without having to eat it all. The sample represents the population of soup. Here's another example of samples. How many of you have sampled ice cream flavors? You use a small sample to make a decision about the cone or half-gallon tub of ice cream that you want to buy. The sample represents, again, the population of ice cream in this case. This is what's done in statistics. Researchers want to find out something about a population or all individuals of interest, but they don't have time or money to study every single subject in the population. So what do? They select a sample, a small number of subjects from that population. They study those subjects and use that information to draw conclusions about the whole population. The main point is that we use sample data to generalize and make decisions about the population we're interested in. Be aware that the definitions of a sample and a population will depend on your perspective. Say that we study the students in your statistics class. If these are the only individuals we are interested in, then we have measured the population of scores. Or, if we are interested in the population of all college students studying statistics, then we've collected a sample of scores to represent that population. But if we are interested in both the population of college men and college women who are studying statistics, then the men in the class are one sample and the women in the class are another sample, and each represents its own respective population. So, a population is any complete group of scores that would be found in a particular situation, and a sample is a subset of those scores that we actually measure in that situation. The logic behind samples and populations is this. We use the scores in a sample to infer or estimate the scores we would expect to find in the population if we could measure them. So, if we observe that greater studying leads to better learning for a sample statistics class, we will infer that similar scores and behaviors would be found in the population of all statistics classes. Because we are talking about samples and populations, we separate statistical procedures, or statistics for short, into two categories which we mentioned earlier: descriptive statistics and inferential statistics. Now, let's take a closer look at the two categories. The main focus of descriptive statistics is to organize, summarize, and display data. Descriptive statistics play an important role today because of the vast amount of data readily available at our fingertips. With a basic computer and an internet connection, we can access volumes of data in no time at all. Being able to accurately summarize all of this data to get a look at the big picture, either graphically or numerically, is the job of descriptive statistics. When you see descriptive, think describe. We use descriptive statistics to answer what is the average score or typical score. Are the scores very similar to each other or very different and spread out? Do scores tend to increase or decrease? When or how? Descriptive statistics can result in a parameter. A parameter is a value that's usually numeric, and it describes a population of scores. They are symbolized using the Greek alphabet. Mu for population mean, sigma for population standard deviation, and rho for population correlation coefficient. Parameters are numerical summaries of a population. Descriptive statistics can also result in a statistic. A statistic is a value, and again usually numerical, that describes a sample of scores. Statistics are symbolized using the English alphabet. capital M for sample mean, lowercase s for sample standard deviation, and lowercase r for correlation coefficient or sample correlation coefficient. A statistic or statistics are numerical summaries of a sample. Statistic versus statistics. Don't get confused because these two terms are used. One, statistics, we've talked about as statistical procedures, and now we're introducing statistic and statistics as numerical summaries for sample data. So just remember that distinction. There is a difference between those two. Here are some examples of parameters. The average age of all people in North America, the proportion of students earning an A in the statistics course, the average SAT score of all graduating seniors anywhere. Examples of statistics, the average age of a sample of 30 students at Pierce College, the proportion of a sample of students in statistics courses who earn an A, and the average SAT score for every 10th exam paper. Notice the difference or the distinction between the two. To recap, the main focus of descriptive statistics is to organize, summarize, and display data. We can do this using tables, graphs, and numerical summaries. The main focus of inferential statistics, which we haven't talked about yet, is to make decisions or predictions about a population based on data from a sample. Inferential statistics are procedures for deciding whether sample data accurately represent the population. Inferential procedures are for deciding whether to believe what the sample is telling us about the scores found in the population. Usually, population parameters cannot be measured directly, or they are unknown, which is why inferential statistics are used for estimating these parameters. The common terminology that we tend to see is margin of error, or that the results are statistically significant. That usually is a clue into, oh, we're talking about inferential statistics. So here are some examples of descriptive statistics. The unemployment rate in California is 4.2 compared to the national rate of 3.9, based on May 2018 data. Approximately 57% of Pierce students identified as female and 43% identified as male. Approximately 62% of Pierce students are under 25 years old. Here are examples of inferential statistics. Based on a recent sample, I am 95% certain that the more hours you spend studying per day, the better your statistics test scores will be. Based on a random survey, the average salary of male employees in a particular job category across the country was higher than female employees' salaries. So you can see, or hopefully you can see, the difference between examples of descriptive statistics and examples of inferential statistics. Key terminology for inferential: based on a recent sample, based on a random survey, right? So those types of terms clue you in that we're making inferences, right? We looked at sample data and we're making a prediction about what's going on in the actual population data.